Hello, I'm Cale Gregory, and for my project, I focused on smoothed particle hydrodynamics, or SPH, for fluid simulation. Fluid simulations have many use cases. For example, in video games, they have real-time simulations. Otherwise, in movies and commercials, they have pre-computed fluid simulations. To implement my project, I followed these two papers closely. On the left is an explanation of the physics involved in fluid simulations and a tutorial on the different types of implementation methods for fluid simulations. On the right focuses more heavily on SPH and the kernel choices made to smooth out these particles and create a more realistic fluid and stabilize the simulation. There are two main methods in implementing fluid simulations. On the left, you see the Eulerian method, or the grid-based method, which measures the flux of the fluid through different gridded cells in a certain area. On the right, you see the Lagrangian, or particle-based method. SPH follows the Lagrangian method as it smooths out these point values to make a fluid. These equations govern SPH. On the left, you see the Navier-Stokes equations. Firstly, the conservation of mass says that the change of mass should be equal to 0. This is held true through the number of particles remaining constant from frame to frame of the simulation. During the sum of forces, you see the change of the vector field and velocity plus some kappa constant times the double derivative of viscosity minus the change of pressure is equal to the entire force on the system. The system is then discretized into these particles and point values such that you can get the density and pressure at these points. Using these points, as seen in the middle image, you can then find the forces acting upon each point and create the final equation of the sum of the forces from these components. As you may have noticed in the previous slide, there is a use of a W function. This would be the kernel function. It is used to smooth out the point values from these particles to create a fluid. On the left, you see the general purpose kernel, which is used to calculate the density and viscosity of the fluid. However, this is not used for the pressure in the case that in high pressure situations, many of the particles will come together and overlap completely, whereas this creates an issue, so we use a spiky kernel where the derivative as it reaches 0 does not go to 0 as in the general purpose kernel. To clarify these functions, the bolded line is the original function, whereas the normal line is the gradient of the original function, and the dotted line is the gradient of the original function. Using the comparison of a low rest density and a high rest density simulation, you can see that the low rest density, as imaged here, is going to make a cuboid shape and push out as the pressure is pushing it away. And it is curving due to the surface tension and slowing down due to the viscosity. In the next video, we see that it'll actually come in because I'm using a higher rest density of about 8.5 versus the previous of about 2. As a result, you see it get smaller and smaller until it eventually comes out. Even though these particles overlap, it is not a problem as mass is still maintained, however, volume changes. This is all done without external forces to verify the inner forces of the fluid simulation. Finally, here is a clip of the SPH with external forces such as a bounding box and gravity. As you can see, it still pushes in due to the pressure, and then it comes out more plumed out at the bottom due to gravity compressing it down. And you see as it fills the box and hits the ground and spreads out as a fluid should.